Bismillahirrahmanirrahim. Can you hear me properly? And the slides are also visible. Okay. As we discussed at the introductory lecture, that whenever you are analyzing an algorithm, there are three scenarios. You can analyze an algorithm in best case scenario, worst case scenario, and average case scenario. And at that point, I also mentioned that most of the time, average case analysis and the worst case analysis give you the same result. That's why usually whenever you are analyzing an algorithm, we analyze an algorithm either on the worst case analysis or on the basis of best case scenario. Last time we started the discussion about theoretical analysis using RAM model, and we take the example of insertion sort, and we perform the analysis of the insertion sort against the worst case scenario, the scenario in which you have to take maximum time to get your solution. And we are in that particular scenario, we assume that this while loop will certainly executed multiple times whenever the data comes. Okay, that was the worst case scenario. If you remember how we can process the data on an array using insertion sort, we discussed this also in last lecture, that whatever the value you found in the second iteration, that second index, that is compared to the previously already sorted data. And you observe that in this while loop, we have different type of and different number of iterations depending on the data. For example, here we have to perform one comparison, one iteration. Here we have to perform two iteration. Here we have to perform only single iteration. Okay, and so on. So the question is, what could be the best case scenario for this while loop? Anyone? No, I'm not talking about the result. I'm talking about the scenario of the data. Which kind of data can achieve the best case scenario in which you have to perform the comparison minimum to minimum possible in insertion sort? Yes. What kind of data will have to perform minimum number of comparison? For example, if you see this iteration, 1 is compared with 6, because 1 is smaller, so I have to continue further and continue further and continue further. What will be the situation when I do not need to perform further comparison? Like this step. When I have 6, which is the largest one, I have to perform only one comparison. Isn't it? So it means if the data is already in sorted order and you call this insertion sort, what will happen? If you start from second index, after making a comparison, you do not need to swap. Then you go to the next iteration, and 3 is greater than 2, so no further swapping. 4 is greater than 3, 5 is greater than 4, and 6 is greater than 5. Isn't it? So if the data is already sorted, then you need the minimum possible number of comparison. And if you have minimum number of comparison to rearrange the value, it means you will complete your execution in minimum possible time. And if I come back to the algorithm, this while condition, if the data is already sorted, this condition will remain always false. Is it clear? So it means if your data is already sorted, that will be a best case analysis. Okay. And last time we concluded the worst case analysis, and the running time was O of n square. That was the conclusion of our discussion last time. Now we are moving to the best case scenario. In best case scenario, if we are following the same algorithm and using the RAM model, what I have to do? In RAM model, if you have an algorithm, which value you must determine before concluding your efficiency value? We have to make two columns, first for the cost and the second for the number of times. So in best case scenario, this while loop, this condition will always be false for every iteration because data is already sorted. So this statement will execute it only once, and because it is part of outer for loop, so its number of iteration will be equal to the statement which coming before this one, like assignment statement I assign j minus 1. Is that clear? So rest of thing is same. This for loop will execute n time. This assignment statement will execute n minus 1. I assign j minus 1, it will execute n minus 1 time. While condition will execute exactly n minus 1 time, because for every value of j, this while statement will be executed exactly once. And if head is executing only one time, definitely inner statement part will never execute because while condition is false. So that's why their iteration is kept 0. And the last, this statement is part of for loop, that's why its iteration is again n minus 1. Any doubt about this thing? This is the best case scenario, and again, if you want to calculate the running time, that will be represented by T of n, and you will calculate it by multiplying the cost column with the corresponding times column. And after multiplying these corresponding value, you will add them up to calculate the total running time. So the equation for the best case analysis will be equal to C1 into n, C2 n minus 1, plus C3 into n minus 1, and so on. If you simplify, there will be some terms with n and some terms will be constant. So we can rewrite this equation like an plus b. And you know, whenever you are writing the efficiency, you will pick only highest order term and ignore all coefficient constant and lower order term. That's why the best case running time for insertion sort is O of n. Any doubt about this best case analysis? Is it clear? So what we have discussed so far about the theoretical analysis, that whenever you are analyzing an algorithm theoretically using RAM model, you have to determine the polynomial function of the given algorithm, and on the basis of that polynomial function, you will pick the value which is highest order term. Why do we ignore the lower order term and the coefficient constant? Anyone? Why do we ignore lower order term and the coefficient constants? We have discussed this point in 204. We ignore these all terms because the maximum value which can be computed, that depend on the highest order term. And the second reason is, for analysis purpose, we just approximate the value. We are not interested in calculating the exact value of running time. We are only interested in determining the pattern of the change with the change of n. So due to these reasons, we ignore the lower order term and the highest order term, because the running time pattern is only dependent on the highest order term. And in 204 we discussed this point in detail, that if you have an equation x square plus 2x plus 10, or you have a equation with x square plus 9. Both equation, although they are not mathematically equal, but from analysis point of view, both equations are considered as the same because their order is quadratic. Is that clear? So yes, whether you are writing x square plus 3x plus 10 or whether you are writing x square plus 3, in both cases the order is same, which is x square. So because whenever you are analyzing, you are only interested in approximate value with respect to big O. That's why we only pick the highest order term. And second reason was that the maximum value which can affect the result of the running time, that can be calculated by the factor of highest order term. And why we ignore the coefficient constant? Because these coefficient constants actually represent the effect of environment, the hardware you have used, the processing speed, RAM, etc. These effects are reflected by the coefficient constant. So we ignore those values also. So basically, whenever you have a polynomial function, you have to pick the highest order term. We want to judge algorithm independent of their implementation. So the effect of the environment should be excluded. That's why we ignore all coefficient constant. And rather than figuring out the exact running time, we are just approximating like with the help of big O. And lastly, the basic idea of analysis is to determine how the performance of an algorithm respond to the change in the problem size. This is the major objective of performing analysis for any algorithm. If you are determining this pattern only, that will be the true sense of representing the efficiency of an algorithm. That will not include the efficiency of environment in it. Is that clear? And this is the same example which we have discussed in detail in 204, that for example, if the function derived is f of n is equal to 4n square plus 3n plus 10, you can see the difference between the function value and the factor which are included in calculating the total value of f of n. So here you can see if you start with n equal to 1, 4n square will be 4, 3n is equal to 3, 10 is 10. But as soon as you keep on increasing the number of instances, number of input, the major contribution comes from 4n square, and all other values are almost negligible as compared to this big value. That's why we pick the highest order term and we ignore the coefficient constant. Is that clear? No, there are many different complexity classes. N square is the one example. Okay, there are many other complexity classes also. Okay, n log n, logarithmic, and so on. So last time I told you that whenever you have an algorithm, you can analyze it in a two way, either using mathematical or theoretical analysis, or you can also analyze an algorithm on empirical basis. Obviously, we will not do the analysis on the basis of empirical study every time. Our experimental analysis will not be carried out every time because it is more time consuming. But to give you an idea and to verify whether you are analyzing an algorithm empirically on experimental basis or you are analyzing an algorithm mathematically, the result will be the same. Okay, so in empirical analysis, as I have told you, that you have to set up a laboratory environment and you have to code your algorithm in some particular language and using some particular hardware. Okay, so in empirical analysis, the time efficiency, when you are collecting, you have to select some specific sample of input and see the variation with the change of input size, how your different experimental setup behave and how the physical time is actually changing with the change of input. Then you will calculate the time in the physical time units like millisecond, second, hours, a day, or so on. You have to use the standard time unit and standard tools to calculate that time. Okay. Then you will, or if you could not calculate the time, then you will exactly calculate how many time an operation is being carried out, and then we can analyze the data which we receive after running multiple experiments on the same environment or on a different kind of setup, and then we can conclude our result. So here is an example in which we have the same insertion sort, and we have tried to execute that algorithm on different hardwares. Okay. For example, if we execute for 2000 integer, if we implement that algorithm and run it on home computer, desktop computer, mini computer, mainframe computer, and super computer, these are different type of computer hardware. So you can see the difference of the time, even though the algorithm is the same, but it takes more time in home computer as compared to desktop, and the best result comes in on a supercomputer in which the 2000 integer values are sorted in 0.087. So now you can observe that with the change of the hardware, the efficiencies keep on improving, but you cannot conclude that the algorithm is performing better on supercomputer as compared to desktop computer. You cannot conclude this one because this conclusion will be wrong. Why it is wrong? Because this efficiency does not reflect only the impact of the algorithm. These results also include the efficiency of the hardware or the environment. That's why this is our first objective, to exclude the effect of these environments. Is it clear? How we can do that? We can somehow reduce the experimenting environment, and we only select two different type of hardware and study the variation in their running time with the change of the input size. So here you can see for 125 input, 125 values of integer values, home computer is taking 12.5 milliseconds and desktop computer is taking 2.8 milliseconds, and so on. And you can observe by change of the input size, as you keep on increasing the input size, these running time is also keep on increasing on different hardwares. Is it clear? Still we are not able to conclude something, what could be the efficiency of the algorithm again. Even we are changing it with the input size and some hardware comparison, we are still unable to exclude the effect of the environment. That effect is still in this result, and they are reflected in these values. Is that clear? Now, how we can conclude our efficiency results, and how we can determine the efficiency of an algorithm? What we have to do? We have to plot a lines or graph against the number of inputs and the running time which it is taking. So if you plot the graph of these values, you can observe that we found two totally different curves. They are produced by the use of these lines, these values, which I have shown you on the previous slide. If I use this data and plot the number of instances, number of input against the time taken by these input size to solve the problem, you can observe there are two different curves generated. This is one curve and this is the second, and still you can find there is a quite big difference between the values of these curves. They are not same. But if you remember, if from a given line, you can easily determine the line equation. If I determine the equation for this line first, f1n, I observe that I have this equation, and for second function I can determine the equation, line equation, this one. Have you ever studied how you can determine the line equation from a given line? I hope you have studied in your mathematics. If you have 2 points on a line, then you can find a equation of a straight line. For example, y minus y1 over y2 minus y1 equal to x minus x1 over x2 minus x1. So there are fixed rules for determining the equation of the curves or equation of the lines. So using that mathematical knowledge, we can convert these lines into a mathematical equation, a polynomial function. Is it clear? Once you have drawn this polynomial function, these equations, now you can see the similarity and dissimilarity between these two functions. You can observe that both equations, although they are different, but their pattern is same. The first equation is also an square plus bn plus c, and the second equation is also an square plus bn plus c, of the same nature. So in all this experimental setup, which thing we kept constant? Whether it is a home desk computer, whether it is a desktop computer, only thing which we kept same was the algorithm. And which thing we keep on changing? The hardware environment and the problem size. Isn't it? So if you compare these two equations, all those things which are common, they are actually representing the efficiency or the running time of the algorithm. And anything which is different, they are actually representing the effect of environment. Is it clear? So from here you can conclude that this insertion sort algorithm, even though if we perform the experimental analysis, the pattern, the equation will remain same. As you observed last time, the equation for the worst case analysis was the same, an square plus bn plus c. Remember? So we have observed a similar kind of equation from the experimental result. Any doubt till now? So if I pick any one of the equation, the first equation, this equation is picked with the a is 0.001724, b and c. If I draw the values and draw the function value and the contribution by the an square factor, you can observe that the maximum contribution is taken from the factor 2 an square, and rest of the terms are contributing very little, and this difference becomes bigger and bigger as you keep on increasing the value. For 2000 data value, you can observe 99.9% of function value is determined from the factor an square. So if even though you have a polynomial function an square plus bn plus c, actual efficiency will be described by the factor an square, and from that even a is actually the effect of environment, the hardware, the environment which you have used. So again we will conclude the running time will be O of n square. Is that clear? So you have observed that whether you are using the mathematical analysis, you are performing the mathematical analysis, or you perform the empirical analysis like this as I have explained you, both will give you the same result. It doesn't matter whether you are analyzing it empirically or you are analyzing the algorithm theoretically. Is that clear? So in addition to the n square class, there are many well-known, well-established efficiency classes. which you may observe while you are analyzing different algorithms, that starts with constant, log n, n log n square, n cube, and n factorial. In this table, the constant will be the best running time. If you design an algorithm whose running time is constant, what does it mean? That the running time will not change with the change of n. If the n is increased, for example, isn't the percentage will be more than 100%? No, that is not the case. How it can be more than 100%? I think you missed some important thing, that this f of n function is dependent on this complete factor. So it will never happen that only this portion will produce more than 100%. Is that clear? Is it clear? So it will be, we are comparing the function with the contribution of an square. Okay. So finally, the best running time for any algorithm is possible constant. Constant means even though you keep on changing the values, number of input, the running time will not change. Okay, as you have an example, if you write an algorithm to search, to access an element in the array. So whether the array consists of 1,000 elements or it consists of 10,000 elements, accessing a particular index will not affect, the time will not be affected. Why? Because in array you can directly access any element. It is not dependent on the length of the array. Is it? So that algorithm to access an element in the array, that will be its efficiency will be constant. Is it clear? Same is the case for hashing. In ideal situation, in hashing, you will directly access the element. You do not need to traverse. You will apply the hash address, and that address will be the location at which the value exists. Is that clear? So the best possible running time for any algorithm is constant, and the worst is factorial. And generally speaking, your efficiency maximum to maximum should be below n cube, and it is more acceptable if you design an algorithm till n square, but in some specific cases n cube is also acceptable. But if you are designing an algorithm whose efficiency is more than n cube, then it is not acceptable, because it will take a lot of time to solve the problem when the number of inputs are too is large. Is that clear? And ideally, your efficiency should remain log n or maximum to maximum n log n. These are the algorithms which are very much acceptable. N square is also good, but n cube is rarely acceptable. If you are designing an algorithm whose running time is becoming n cube, try to reduce it and redesign the algorithm so that you can reduce the running time. Is that clear? So these are just some examples. Few examples you have already familiar with. Quick sort, heap sort, merge sort is n log n, radix sort is n, and selection sort, insertion sort take n square time. So this table will give you an idea how these complexity classes are significant towards the selection of an algorithm. For example, if you design an algorithm whose running time, for example, n square. So you can imagine that if you design an algorithm whose running time is n square, and second algorithm you have designed whose solution is 2 raised power n. So what will be the difference of the solution only for 256 value, you can imagine that this algorithm will take only 65.5 millisecond. Whereas if the same problem with the same number of input is solved whose efficiency was 2 raised power n, it will take 3.7 into 10 to raised power 63 years. So obviously you will never select an algorithm whose efficiency is exponential, 2 raised power n. Is it clear? So that's how, by looking at a complexity class of an algorithm, one can easily decide which algorithm is suitable for their problem. This is the significance of these complexity classes. Any doubt, any question? Similarly, there is another table which is again showing the same thing, that with having different complexity classes, what will be the effect of calculating the values for different input sizes. Is it clear? So as we have discussed earlier, and even in 204, whenever you are writing an analysis conclusion of your efficiency value, you will always write it in approximate way, using the order. What is the order of the time? And this order of growth is represented, one of the notation you are already familiar is big O. Okay? And this growth order is just give you an idea with the change of n, how the value will be changed. If n is approaching to infinity, what does it mean? Whenever you are describing the efficiency of the algorithm is described for a reasonable larger size. Because for smaller size of input, all algorithms should be will look like behaving same. Okay, for example, if you have 10 elements and you apply whether insertion sort, selection sort, merge sort, heap sort, any sorting algorithm you apply with 10 values of input, you will observe that they are all sorting the data in the same time. Actual difference is clear when you have a large size of input. Is that clear? So basic idea is of analysis is our order of growth, and determining the order of growth is how the running time will change with the change of input size. So this is all about the analyzing the iterative algorithm. On the similar ground, some exercises are added here on the next slide. I'm leaving it for your own practice. For example, this algorithm is given for selection sort on the same pattern as we have done for the insertion sort. So this is your exercise. You should go through these and perform analysis. If you found any problem, then you can discuss it with me in next lecture. Similarly, another example is given for your exercise, that is linear search. So again, it is the very similar kind of algorithm. Informally, we have already analyzed the linear search, that the running time will be linear. But using RAM model, how you can analyze, you have to draw two columns, cost and times, and then you will calculate how many times these values will be executed, and try to perform these all analysis in detail using RAM model. Okay. Similarly, the next example which is given for your exercise is maximum element. Some informal analysis is already given. You can analyze it formally using RAM model. This analysis, informal analysis, is given for your reference. Okay. Similarly, next algorithm is unique element problem. Again, some informal values are already given, but please try to analyze it yourself, this algorithm first, and then go to the comparison and finding the results. Okay, its further calculation are also given here for your reference. Is that clear? So on this weekend, you have a lot of exercises to perform, but it is very simple. It will not take much time. You can randomly, I will suggest, at least try to solve one class exercise and one home exercise by your hand, okay? At least one. But if you have time, then you can try as much as it is given in the on the slides, okay? So by end of this lecture, you may find some review question also in form of MCQs that will help you out to review the concept which we have discussed so far. Is it clear? So I think we should stop till this point. Inshallah, we will start with the recursive analysis next time because it is a relatively big topic. So I don't want to start it now. So use this time, the remaining time, for yourself, self-study for the, solving these exercises, home exercises as well as class exercises. If you have any question, you can ask me. Otherwise, I will mark your attendance.